Okay, so the first talk is by Mohan Ravichandran, and he will talk about circular fence posets.
So I'll be using a Blackboard talk. We can turn it off and maybe you can lift the screen. So I'm going to be talking about something quite elementary, something that I think everyone should be able to grasp immediately. You might accuse me that the talk is maybe too elementary. What is this for? But I really think that there is a lot we don't understand. That I'm sure that there are basic extensions and generalizations that hopefully we could talk about. So the result is started like this. So I was interested in these class of posets called fence posets that come up in a few areas. I'll tell you about them. And while studying them, we came across a very interesting phenomenon of infinitely many pairs of polytopes that are non-isomorphic, but for some reason they have the same Ehrhart polynomial, so which contain the same number of lattice points, and dilates contain the same number of lattice points. I'll tell you what these things mean, and but I can say that this is a surprising phenomenon. There are a couple of such examples in the literature, but this one seems to be new. The nice thing about this talk is that I can directly tell you what the result is, even before I motivate what this comes from, where this comes from. So suppose we have a collection of natural numbers, a composition, and let's say that there is some other number alpha. Okay. Okay. Now I'm going to define the following polytope. So this is a polytope, which is defined in the following way. So this is the set of all points in, so this is, so it is going to be a subset of the unit cube. Sorry, maybe. So you have a cube, but then you slice off, you have these additional inequalities that look like this. So this is just the cube, and you're cutting it out by when I say mod s. So when I have s plus 1 should be taken to be 1, right? So in 2 dimensions, I mean, so if you look at a simple example, this thing is going to look like this. It's a very simple polytope. In 2 dimensions is something very simple. So it's a cube, and then you slice off 2 sections. In the higher case, so you have sort of a dilated s cube, and then you cut off these hyperplanes, right? Now. The result is, so this seems to be a very basic object, and indeed it is, but the result is something that I still find quite striking. So this is s is equal to 2. So this is one example when s is equal to 2. Yeah, and then you take, you chop it off. Now, I suppose I have a new parameter. What I'm going to do is I'm going to look at slices of this polytope along this particular hyperplane. So this is, okay, and then intersect with this hyperplane. So in this case, the hyperplane is just going to be this. Okay. So you take hyperplanes. This is x plus y is equal to t, and then you take a slice with a hyperplane, summation xi is equal to t. Yeah. Yeah, HLT as a t parameter. Yeah. So now, with just a simple introduction, I can tell you what the result is. So the theorem is the following. So we will make some assumptions. So we'll assume that for simplicity, so this is a natural number. This is a composition of natural numbers. So the theorem is that, so assume that with the same notation that So you could just think of alpha to be equal to 1 and all these AIs to be bigger than or equal to 2. I mean, that captures the essential complexity of the problem. Okay, then we have that. So this entire, you have the entire polytope, and you're looking at sections of the polytope. So this polytope, by the way, is not symmetric. It's not centrally symmetric. So I mean, there is no point so that, you know, I mean, so it is not the case that there is some barycenter so that if, you know, if a plus x is there and a minus x, it's not a symmetric polytope, right? So then the result is that, and then we'll use this notation n to be plus s. Okay, I'll tell you where this comes from. There's a natural reason where this comes from. So then for any natural number, one has the fact that, you know, that these two polytopes and so there's a slice and there's a complementary slice, right? So they have the same number of lattice points. They have the same volume. Every dilate of this will have the same number of lattice points as the corresponding dilate of this. So
sorry, I have a question.
Yeah.
What is that superscript T? What does that indicate?
Yeah, so we are taking this this entire polytope and we're taking a slice of this polytope in this direction, 1, 1, 1 direction. So perpendicular is all one vector.
And T represents T's I mean, what does it represent? What does T mean? I mean, T stands for what?
Well, T. T is some parameter. T is just some parameter. I mean, we'll see. I mean, so I'll give you a combinatorial interpretation of this. That T will have a very clear meaning.
Okay.
Sorry, and what was N? Was that S?
N is so this thing. So you have this composition A1 AS. Okay, it is a summation of the AI plus, you know, 1 taken S times. So summation AI plus 1. Yeah.
Sorry,
so they have
the light is too strong, so I can't see.
I'm sorry. Yeah. So they have the same. Okay. Yeah. 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 So maybe I'll. Yeah. Okay. Yeah. Oh, just for simplicity. I mean, pretty much everything holds. I mean, you have to modify the statement appropriately, but then I want to keep the technical details to a minimum. So they have the same Ehrhart. I'll tell you what these are, in case you haven't seen this in a few minutes. Okay, right. So the thing is, yeah. So this polytope is genetically not isomorphic. Okay. So this thing I should quickly mention that I mean there is a very there is a famous result due to Stanley that people working in combinatorial love. So Stanley, what he did, so I won't go into details, but this is a really fun paper. So Stanley, what he did was in 1986 to any poset, he introduced two polytopes. So one polytope is called the order polytope, and there is a polytope called the chain polytope. Okay. Let me not give the definition, but then they are elementary objects, and then they are non-isomorphic, very far from being isomorphic, but then miraculously they have the same volume. So, and not just the same volume. So these are polytopes. The number of lattice points is the same in dilates, etc. So let me just say that for simplicity. So I'll use this notation consistently. When I have a polytope, and when I say this thing, absolute value is the volume or the relative volume. If the polytope is a 3-dimensional polytope in a 5-dimensional space, then it's the 3-dimensional volume appropriately computed. So this is, I mean, this is a really beloved result in polyhedral combinatorics, and it has seen lots of extensions, including one by Arvind from a few years ago. Yeah, so it's striking because the polytopes are very different, and in this case, the way that this equality is proved, it is proved in the following very nice way. So given any polytope, there is this notion of a triangulation. So you take a polytope and then you split it up into simplices, so that the vertices of each of these simplices is a subset of the vertices of the polytope. So I mean, the triangulation is what you think it is, right? So this will be a triangulation. Okay, and then what Stanley showed is that both these polytopes, they have triangulations that all the simplices have the same volume. So this is called a unimodular triangulation. And he gave explicit unimodular triangulations for this as well as for this. And then the number of unimodular triangulations of both these polytopes is related to the number of linear extensions of the partial order. Okay, so the point is, he used the existence of unimodular triangulations and a calculation as to the number of simplices in this triangulation to show this equality. But this one seems to be a bit different. As I mentioned in the abstract, the reason why these things are the same doesn't, I mean, we have been trying to understand it from a geometrical perspective, but we haven't gotten there yet. Okay, so
I have a question. Can you give a two-dimensional example of a unimodular triangulation?
Well, I mean, you could take a regular hexagon or something, right?
Regular hexagon.
A square, for instance, yeah. I mean, unimodular triangulations are rare, by the way, I should say. They don't always occur, but then when you find it, people get delighted. So because it suggests that there is some interesting algebra in the background.
So in the 2D case, there's only the square, right? I don't think there's anything else.
Oh, you might be right. You might be right here. In the two-dimensional case, you only have the square. You don't have anything else. But if you want the vertices to be subsets of the vertices, that's possibly true. Yeah. So, yeah, possibly. Yeah, I mean that might be the case. Okay, right. So, yeah. So there are three parameters here. So there is a composition, there is a shift alpha, and there is this t. So I mean, generic in A as well. Generic in A as well. Yeah. Okay. So where does this come from? So this comes. We chanced upon this when we started looking at these class of objects called fence posets. I mean, for people who have worked in quiver representations, cluster algebra, so these objects will seem familiar. So I mean, instead of formally defining them, let me just give you an example. So it is a definition by picture. So, so this is going to be a post. So this is the base set. So the base set is 1 to 9, and this means that you have an order relation. Okay, so this means that 1, 2 are less than 3, and then 4, 5 are also less than 3. 5 is less than 6. 7, 8, 9 are less than 6. Okay, so these are the order relations in this particular poset. It's a relatively simple poset. One is sorry. Maybe I should say yeah. So each chain will give you 5 is less than 4 is less than 3. 5 is less than 6, and yeah. So now, given any poset, one thing that people often look at is that they look at lower ideals. So a lower ideal is a subset, so that if an element belongs to the subset, anything smaller also belongs to the subset. So let me write down a lower ideal of size 1, one of size 2, and one of size 5. Okay. So this is a lower ideal of size 1. Okay, anything smaller than 5 is the minimal element. 1, 5 is also a lower ideal, and you can check that this thing is also a lower ideal. This is a lower ideal of size 5. Okay. Now, the rank sequence of this poset. Before that, I should say that if you look at the set of all lower ideals, it forms a distributive lattice. Okay. and it has a natural grading, the number of, see, the poset itself is not graded. Okay, we're not looking at the poset itself. We are looking at the collection of lower ideals, in the poset. Okay, there's a
Sorry, what's the lower ideal? Could you explain?
It's a subset of the base set.
Okay.
So that, so if some element belongs to the subset, then anything smaller than that element also belongs to the subset. Yeah. So for instance, 1, 4 is not a lower ideal because 5 is less than 4, but 5 is not in the subset. Yeah. So the rank sequence or the abuse of notation or the rank polynomial, it is just going to be summations. You have a formal parameter Q. I is a lower ideal. Okay. So for instance, just so that we know what we're talking about. So if you compute the rank sequence or the rank polynomial for this, so there is one lower ideal of size 0, 2 lower ideals of size 1, and then lower ideal size you have 1, 2, and then you have 1, 4. Of size 3, you have 1, 2, 4. And size 4, you have everything. Okay, so this is going to be a rank sequence. Maybe you would write it as 1, 2, 2, 1, 1. Okay. Right. Now,
I have another question.
Yeah.
So in that 1, 4, 5, 8, 9, why isn't it 2, 1, 4, 5, 8, 9?
Yeah, because so if something belongs over here, anything smaller than that must also belong.
I
It doesn't
can't
say anything about anything larger. Yeah, yeah. Okay.
Sorry.
So you had a question about.
I was just saying that this is confusing terminology because rank generating function is something slightly different, right? It's the number of elements that are fixed.
Right. But that's what I mean. So, but this is so what you do is you start look at a poset, and then you look at the distributive lattice of lower ideals.
So it's
and that is also a poset.
Yeah. So this is the rank polynomial of that.
Of the ideal lattice, if you wish. Yeah. Okay. So now this thing, by the way, so this has a natural interpretation in terms of quiver representations of type A, but let me not go into that because it won't add anything to the result. So these things. Yeah. So if you take a type A, if you take an AN, type A Dinkin diagram, and then you take a quiver. So that means you orient the arrows appropriately. And then what you do is you look at irreducible sub-representations. And then how many sub-representations of dimension 1 you have, of dimension 2 you have, and so on and so forth. So this is exactly. Yeah. So these things come up in that context as well for type A, right? So now the conjecture was that, and this is something that we proved last year. So this is a conjecture due to it came up in some spectacular work that I'll briefly tell you about. This is the conjecture was due to Moria-Ginu and Valentin Ovsienko. Is that for any poset, this sequence, okay, this rank sequence is unimodular. So I'll use this notation, maybe I'll just say R of alpha. Okay, I would like to say that it's a rank sequence of alpha. So if you don't mind, I'll skip the Q. Alpha is, so you start off, sorry, I should say this thing. So this thing, so how do you encode this? So you encode this in the following way. So you have a up step of size 2, down step of size 2, up step of size 1, down step of size 3. So any composition will lead to a fence poset. Okay, so then you can understand the fence poset in terms of, okay. So if alpha is a composition, then you have that R of alpha is unimodular. And this turns out to be true. So we proved it together with Esgi. So now this is the theorem. But this is not what I will be talking about today. Though I should say, there is a beautiful reason, why these things come up. And I'll briefly mention that. So we all know, I mean, we've all seen these Q deformations of the integers. If n is an integer, so we define the Q deformation to be Q to the n minus 1 by Q minus 1, which is just, I mean, Q is 1, it's n, right? But then, and this is something that comes up everywhere in enumerative combinatorics. If something counts something, then the Q version typically counts the same thing with additional structure, right? So it's bread and butter. Now, remarkably, one would have thought that such a thing would have been asked 200 years ago. Yeah.
So can you explain that theorem?
Yeah.
What is that R plus?
Yeah. So R alpha, so I look at this composition 2, 2, 1, 3. I have a fence poset. Okay, and then I look at the lower ideals. So in this case, we saw that, okay, in this case, so this composition is 2, 1. I start off with the composition. I look at the associated fence poset, and then I look at the number of ideals of size 1, size 2, size 3, and so on and so forth. This sequence increases and decreases. So that's the conjecture.
So what does K stand for?
That's the co-author. Sorry. And that's me. Oh, sorry. So now one would think that, yeah, fine. Yeah, Q deformation of natural numbers. I mean, we use it, we have it for breakfast, we have it for dinner. But then what about rational numbers? Is there a natural notion of a Q deformation of a rational number? Right? So see now, notice immediately that this is not the correct thing to do. So you should not do this is meaningless because 2R by 2Q is the same as, I mean, 2R by 2S is the same as R by S, but this object will be different. Okay, so this is not correct. And another thing that you could do is you could do the same thing, right? You could do Q to the power of R by S minus 1 by Q minus 1. You could do this, but then you end up getting, and you can think of it as a power series, but you end up getting a power series where the coefficients are not integers. So you're not doing combinatorial solution. Okay.
Sorry,
so
why is RQ by SQ the same as 2RQ by 2SQ?
No, it's not. I mean, never, apart from some trivial cases. Yeah. So that's interesting. Okay, and the amazing thing is that there is a beautiful theory that was developed just 2-3 years ago. Okay, and so there are a few different ways of defining this, but then, so this is again due to the authors, Moria, Ginu, and Ovsienko. So the original construction, goes like this. Okay. So what you do is, so you look at a continued fraction expansion. And you arrange it, okay, so that you have 2m parts. So to give an example, if you have 32 by 9, if you haven't seen continued fractions, then, I mean, please do see them because they are. So this thing can be written as okay. So the traditional notation is that we would write this as, so the thing is that this has the property that AI is an integer, positive or negative, and the other, sorry, A1 is an integer, and AI is bigger than or equal to 2, bigger than or equal to 1, sorry. So any rational number has a unique continued fraction expansion that has lots of very nice properties. So the notation would be, the classical notation would be 1, 1, 4. So this is how you would write this. Okay. Now what they did is they did something which is, I mean, you ask, I mean, where did they get this from? So they give this following definition. I'll give another nicer definition a little while later, but this is the original definition. So then they defined this thing to be this. So this is your regular, so it's integer. So it's a regular, Q integer. Now you have to be a bit careful here. So for even odd parts, you take the Q integer. Even parts, you take Q inverse. Okay. So in this particular case, for instance, so you have that 32 by 9. If you work it out, then, okay, you get a complicated expression. Maybe I shouldn't write down this, but let me give you a couple of examples. So before saying that, so this thing is always going to be a ratio of two polynomials. And both these polynomials will have integer coefficients. And secondly, if R by S is positive, both R of Q and S of Q will have non-negative integer coefficients. So let me give you two examples. So this is by 1 plus Q. This is okay, so notice this thing, the numerator and the numerator is 5 in both cases, but here the numerators are different, right? So the numerator will depend on both R and S. Similarly, the denominator will also depend on both R and S. So it's not just something that you compute for the numerator and something that you compute for the denominator. Okay. So the main properties are, if R by S is bigger than 0, then this numerator and denominator polynomials have non-negative integer coefficients. Okay, and here is another spectacular property, that if you have a sequence of rational numbers that converge to a real number, okay, then this thing, so I'll use so Rn by Sn, I'll say capital Rn by, then this thing, then what you do is, see, this thing, right, you can also write it as a Taylor series. Okay, and the Taylor series will have integer coefficients. Okay, then what you have is, then the Taylor series of Rn by Q by Sn by Q stabilizes. So what that means is, okay, I mean, at level n, you have some Taylor series, but then if you look at the kth coefficient, eventually the kth coefficient will become stable, become constant. So to any real number, you can attach sort of a Q-deformed version. Okay, so this is absolutely spectacular, absolutely amazing. And then, yeah, so there are many more properties that have improved.
Sorry, and should also one of the properties be that if Q equals 1, then you actually get the.
Oh yeah, absolutely. Yeah, of course. Yeah, then when Q is 1, then yes, absolutely. Yeah, for the degrees, it's a little bit complicated. It's not. I mean, one has to. I mean, there is no very easy and simple description as far as I know. Right. So
the same question apply for alpha as well. If Rn, I mean, if you look at, since these things stabilize, if you evaluate that at Q, then do you get alpha itself for every real number alpha?
Yes, absolutely.
Can be centered anywhere. These are rational functions. So, what's the center for the Taylor series? It could be anything.
No, but in this case, oh, I'm sorry. So the Taylor series will have a rational coefficient. I'm sorry, not integer coefficients. I mean, so the rational function, yeah, the ratio of two polynomials. Right now, the Taylor series around 0.
Around 0. Okay.
Yeah, sorry, and then you'll have yeah, you'll have rational coefficients. That's correct, not integer coefficients. And also, just like continued fractions, continued fractions of, say, for instance, E has lots of interesting properties. I mean, there are similar things all kinds. So there is very nice in parallel theory, lots of open questions. So this is still work in progress. The writers, I mean, the authors have written up a lot of follow-up for. But anyway, so the point is, the authors also showed that these polynomials that you get, right, this is R of Q and S of Q, that they, in a very natural way, that they are these rank polynomials of fence posets. So they observe that these polynomials are, they seem to be unimodal. And then they observe that they can also write them as, this and this independently can be written as rank polynomials of certain, fence posets. And then they said, okay, is it true that they're unimodal? And this is what we had proved. But what I want to talk to you today about is the following thing. So in our proof, the main idea in our proof, was the following thing. So we introduced this class of circular fence posets. So these are similar to fence posets, but with the difference that, so if I look at 2, 2, 1, 3. Now what I do is I identify the first element and the last. So you have a composition with even number of parts. So I look at the associated fence, and then I identify the first element and the last element.
So did you say that they prove that Rn and Sn are always rank polynomials of fence posets?
Yes, that's correct. They prove it, and it's using they in terms of the continued fraction expansion interpretation. It's a nice proof. Yeah, it's known. Yeah. But yeah, I mean, there are issues about how canonical it is and so on and so forth. But that's a different story. Okay. Yeah. So in this case, so this is the same thing as a fence poset, but with this additional thing that this what was 9 over there is the same as 1. So if you wish, maybe you should draw it like this. So you see, I mean, it's a very simple object. Okay, but then one thing happened. We started making some calculations. I mean, so we were when trying to prove that conjecture. So I mean, we tried a number of different inductive approaches, and then we chanced upon these, and then looking at them, we observed, computationally. I mean, at least Sage told us that for circular fence posets, the rank sequence is always symmetric. So I'll use this, since I'll say this, so CFP is circular fence poset. The rank sequence is always symmetric. Now, this is a very basic object. It's a very simple poset, easy to understand poset. And when you say that, okay, so for all these posets, you have something symmetric, that means maybe there's a very simple reason. Maybe you just, maybe there's some, it's just a matter of flipping it. Maybe there's a natural isomorphism. Okay, but it turns out that is not the case. So here, what is this? Here is a restatement. So the number of lower ideals of size k for any k. So if you take now, what it is saying is that it is symmetric. So the number of elements is n. So you take a lower ideal of size k. Okay. It says the number of lower ideals of size k is equal to the number of lower ideals of size n minus k. But what is this? If you take any lower ideal, say of size, okay, so this is a lower ideal, take the complement, that is going to be an upper ideal, right? So this means that this is equal to the number of upper ideals of size k. Okay, so it's very simple. So you have circular fence poset, you have the lattice of lower ideals, you have the lattice of upper ideals, and the rank sequences are the same. But the interesting thing is that these posets, so
upper ideals need not be of the same size as k, right? I mean, in general.
Yeah, so this is of size n minus k, so you take the complement that will have size k. So where n is the total number of nodes, everything excepting this, right? So what is left over? The remaining k elements. Yeah. So, but then, so this is really interesting. That these posets are not isomorphic. So which posets am I talking about? So the lattice of lower ideals. It is not isomorphic. It is not order isomorphic to the lattice of upper ideals, excepting in some trivial cases. Yeah, so that means that, yeah, so somehow, I mean, these things, you know, the rank sequences, they behave in the same manner, but it is not for some obvious reason. So later, you know, we came up with some, you know, complicated, you know, inductive proof. And then for a while, so the thing is, so this is so we came up with an inductive proof, SZ and myself. And then later, actually, we spent a lot of time trying to find a bijective proof. So, I mean, and then I probably won't have time, but then I wanted to show you some examples of how the bijection can be, or any kind of bijection that exists must actually be quite tricky. And finally, so around 6 months later, Elizalde and Sagan, they did come up with a bijective proof. But I think it is completely fair to say that it is some very complicated bijection. So such a simple object, such an obvious, I mean, it's easy to understand statement. The only proof that they can come up with is a very beautiful bijection, but it's highly non-trivial. You wouldn't expect something so non-trivial for something as relative. So that means that this is a very interesting fact. So this is a few months ago. So they gave a bijective proof.
Sorry, what is the theorem?
So so the theorem is this. So let alpha be a composition of even length, and this will lead you to a circular fence poset. Okay, so it goes up by size alpha 1, goes down by size alpha 2. Then what we have is, if you look at this thing, summation q to the power of I, that I is a lower ideal. So this is the rank polynomial. Then this rank polynomial is symmetric. So to give an example, if you look at this thing, okay. If I'm not mistaken, then the rank sequence turns out to be 1, 2, 3, 2, 3, 2, 1.
And by rank sequence, what do you mean exactly?
Yeah. So if you you look at, so the number of lower ideals of size 0 is 1. Number of lower ideals of size 1, you can take this or you can take this. So there are 2 lower ideals of size 2. How many lower ideals of size 3, size 2, sorry, 2 lower ideals of size 1. How many lower ideals of size 2 do you have? You can have this and this. You can have this and this. Or you can have something or something, or you can have this and this. Yeah. So we are counting the number of row, I mean, so this thing, the coefficient of q to the power of k is the number of lower ideals of size k. And what this theorem is saying is that the number of lower ideals of size k is the same as number of lower ideals of size n minus k, or the same thing as saying that the number of lower ideals of size k is the same as the number of upper ideals of size k. And the curious thing, which which really got us interested, is that there is no obvious proof of this. Okay. Now, okay. So then, I mean, there is something obviously that's much more complicated, but there is something somewhat analogous that occurs in the study of partitions. So there are many interesting, I mean, obviously, that's a huge area, and then lots of fantastic, partition bijection, non-trivial bijections. And in many of these cases, looking at these partition bijections from a polyhedral perspective has proven to be very interesting. So what you do, so these are saying that, that you have 2 sets that have the same size. I mean, for every n, some partitions of some kind, partitions of other kind, they have the same kind. What some people have done, Sylvie Cotil, Igor Park, they have said, okay, we interpret these as the number of lattice points in some polytope. Okay. Now, that means that so you have two polytopes which are different, which have the same number of lattice points. Can you say, is there something more refined that you can get? Another thing that you would like is that, okay, you want a bijection, but then can we somehow make it a geometric bijection? So you want a piecewise linear map, from this polytope to the other polytope that preserves volume, for instance. Okay. So then obviously that gives a lot of structural insight. So then this thing, we started, trying to find, but here in this case, it's very easy to come up with a polyhedral model. So what is it? So let me, so suppose you have a poset, that looks like this. Okay. Let's say. So there are a couple of subtleties over here. So that's why we had to jump through. I mean, this is why we had to do what we'll do right now. So this thing. So okay, the first guess would be what you do is you look at all. Okay. You look at so lower ideals are subsets, right? So you have this. You have this poset on n. Any lower ideal. So you look at the indicator function. Okay, so everything is, if you have a poset on n sets, on n elements, so the lower ideal, so whatever elements you have, you put a 1, elements that you don't have, you put a 0. So it's some indicator vector, and everything is lying in Rn. Okay, now what you could do is you could take the convex hull. Okay, so the first try was the following thing. So so any lower ideal, so it gives an indicator function, indicator vector. In R to the power of n. Okay, so I mean, in this case, I mean, all I'm saying is that if you take this, so this the vector is indexed by 1, 2, 3, 4, 5, 6 elements, and then if you take this lower element, 1, 1, 0, 0, 0. Okay. Now, what you could do is, suppose you look at this polytope pk, which is the convex hull of all the indicator functions. So let's call the indicator vector fi. So if you look at the convex hull of the indicator vectors of all lower L's of size k. Okay.
Sorry, what's an indicator vector?
Yeah. So I mean, all I'm saying is that so you have a polytope on 6 elements, and suppose I look at a subset 2, 3. I send it to in the position 2, position 3. I have 1. In all the other positions, I have 0. Right. So then you could do this, and similarly. So, so what this is saying is that, so the theorem says that I'll use this notation for the number of lattice points. Okay, so then the number of lattice points is in pk is equal to the number of lattice points in Pn minus k, right? These polytopes will not be isomorphic in general, okay? But then in polyhedral combinatorial, the next thing you ask is, if you look at are the volumes the same, for instance? The number of lattice points are the same, but is it true that the volumes are the same? And generally, no. Okay. So we had to come up with so sort of, I mean, coming up with a satisfactory polyhedral model. So we had to think about it for a while, but then we realized that the following thing can be done. So let us only consider this thing, compositions of the following kind. Okay, so let's look at. So Elizalde and Sagan, they call these gates. So these are compositions of the form A1, 1. So up steps are of size A1, A2, A3, and down steps are of size 1. Okay. I mean, all down steps are of size 1. Okay. Now, the thing is, this is not too specific, because if you allow up steps of size 0, so what is, see, imagine, so what happens if, let's say you have, so this is saying that, there is an up step of size 2, down step of size 1, up step of size 0, down step of size 1. Okay. So all this is saying is that if you permit zeros, then you can get, all possible fences, okay? All possible circular fences, okay? So this thing, But in this case, there is this thing. So this polytope, I'm sorry, I won't have time for a discussion, but this polytope that, this is exactly the polytope that I had written down. So what is happening here? So if you look at lower ideals, so let's look at this example. Okay, so given a lower ideal, so I mean these segments are of size 1, so it doesn't matter. Okay, how many segments do you, how many points do you have over here? So you have that, the number of points can be 1, 2, or 3. Okay. Here too, so this is x1. So this is number of points in the lower ideal, number of points you have here, number of points. Similarly, the number of points is less than or equal to x2 is between 0 and 3. But there is one more thing. If you only have 2 points here, then there is no condition. But if all the 3 points exist, then this point has to be present. Now, the thing is, fortunately, you can write this as a linear condition. So what is the linear condition? That x1 minus x2. So if this is 3, this has to be at least 1. So this is less than or equal to 2. And in the general case, you can't encode this as a linear condition, but in this case, you can. So if you put it all together, then you exactly end up with this, right? So here, maybe let's say you take alpha to be equal to 1. Okay. So there is a slight switch over here. So here the condition would be 0 less than or equal to xi less than or equal to ai plus 1. So if you have steps of size ai, it can be up to ai plus 1, and then xi minus xi plus 1 is less than or equal to ai. So this is, I mean, I'm calling this ai over there, and this is, ai plus 1 minus 1. So you exactly end up with this polytope, right? Yeah. And in this case, something very nice happens. So first of all, okay, we checked in Sage. It turns out that the theorem is that, so let me write down this theorem carefully. So I'll say a little bit about these polytopes, and then I'll mention the theorem. So recall that, but these will all have to be integer, but now we relax it. So we think of it as a polytope. Let me just say, let me call it 1. And there is one condition that is required over here, which let's say, I mean, if you think about it for a bit, this must be necessary. Okay, but again, as I said, you think of this as 1 and think of these as AIs as being at least. So in this case, when this is 2, what this means is, these segments have size at least 1. So I'm sorry for the mix-up, but this is, I mean, this is the case that we should be interested in. Okay, good. So then, yeah, and then n is the size of this sort of the tens poset where it came from, which is summation ai plus 1. So this is summation ai plus s. Okay. And then the theorem says that not only, so we know that if t is an integer, so this we've already seen. This is the number of lower ideals. So this is equal to the number of lower ideals in n minus t. But not only that, the volumes are all the same. Not only that, this thing. So we have this notion of the Ehrhart quasi-polynomial. So I have maybe, I'll be done in 2-3 minutes, okay? So the Ehrhart polynomial is the following thing. I mean, if for people who haven't seen it, so suppose you have a polytope whose vertices are lattice points or integer vectors, okay? So there is hope for all of us. This theorem, by the way, this is again, so k goes to, now the dilate of the polytope is just, you just blow it up, by a, the linear inequality, you just blow everything up by k. So the number of lattice points in k times p. Okay, again, I mean, so when k is 1 is the number of lattice points, when k is 2, the number of lattice points in the second dilate, and so on and so forth. This agrees with a polynomial which we will call Rp. So what this is saying is that the Ehrhart polynomial of p evaluated at an integer is equal to the number of lattice points in n times p. Okay. Okay, and also one of probably my favorite theorems in combinatorics is that, okay, there are lots of theorems, and this is what I mean called reciprocity theorems. We have a very nice understanding of what Ehrhart polynomial and negative integers mean. Okay, so it's a gorgeous branch of combinatorics. Yeah. Anyway, now if the polytope is not a lattice polytope, if it's a rational polytope, so you cannot expect it to agree with a polynomial. See, here's a very simple example. If we just take 0, half, so the number of lattice points in n times p, it will depend on whether n is even or odd. Okay, so this is going to be n by 2 plus 1 if n is even, and it is going to be n by 2 plus half if n is odd. Okay, so there is a periodicity that will enter, the arithmetic thing that will enter. And so this thing, so there's a similar thing, but then if you have, instead of a lattice polytope, you have a rational polytope, then you get what is known as a quasi-polynomial. Okay. And then the theorem is that they have the same, so these polytopes, they're not lattice polytopes, so they will be half integer. Okay. Then they may have, the vertices will be either integers or half integers. I'll just say it's half integral. And the theorem says that they actually have the same Ehrhart quasi-polynomial. Sorry, so I'm really sorry. I may not have time to tell you about the proof, but the proof, our original goal was to come up with a geometric proof, a proof that involved concepts such as triangulations. We did not do that, but we converted that into a different combinatorial problem in which it's a problem that counts ideals in a much more general class of posets, and one can carry it out, but one now has to use some linear algebraic tools. Okay. So let me briefly say a couple of things over here. So do you have any comments?
I have a question. So you said 2 alpha is less than or equal to min AI is the necessary condition. But earlier you said that gates can become arbitrary posets by allowing zeros in the AI.
Okay, that is okay. You caught it. There are a couple of tricky things that I was okay. In the case, okay. Well, thank you very much. You brought up an important point. So there, you will have equality of volume. You may not have equality of Ehrhart polynomials. So I mean, I should have been more careful there. Yeah. Yeah. So what Arvind mentioned is that these are special compositions, but these are general if you assume these AIs to be 0 as well. But if you assume these AIs to be 0, then this condition that we had over here, that so there was this condition that alpha. You have this condition. So it's a sort of a non-degeneracy condition, but that does not hold anymore. So, I mean, you're right. Okay, so maybe I should say that, yeah, okay, maybe. However, by using a limiting process, I'll say that the volumes are the same in general. Thank you. Yeah. Well, I mean, obviously, so by the way, this about the Ehrhart polynomial, the highest coefficient is the 1. So equality of volumes is a much weaker statement than saying that the full Ehrhart polynomials are the same. Yeah. So this thing, I should mention one thing that this is sort of within a line of research. I mean, there is a circle of problems related to these posets, corresponding to Young diagrams. So there is let me just end with this famous, again, bring to your attention a famous and beautiful problem that has been open for the last 30 years. So, if you ask me, how is this relevant to what I told you about, maybe we can talk offline. So the conjecture is the following. So what we are doing over here is related to the following thing. So let's say you take a box, okay, as an A by B box. And let's look at a poset of Young diagrams that sit inside. So Young's lattice, but restricted to the box, okay? Now, if you look at this thing, what is the lower ideal, okay, over here? And so this is a natural poset. Poset in terms of, the order, X and Y order. So this thing, a lower ideal is going to be exactly a Young diagram. Okay, this is what a Young, so then if you look at the corresponding polynomial in this setting, this is exactly this is the famous Gaussian binomial coefficient. So it's a polynomial, and Sylvester proved that it is unimodal. It is symmetric in this case because we have a nice symmetry. Sylvester showed that it is unimodal. And then a famous combinatorial proof was given in 1990. So this was proved by the way, never tired of saying this, but you should really go and have a look at this paper of Sylvester where he proves this. It's really, the first page is spectacular. He basically says that now, I will prove using just human reason something that was thought to be impossible, that kind of thing. It's very bombastic, it's great. And O'Hara gave a lovely combinatorial proof in 1990. Now, the following question is still open, and it is very likely that it is true, that if you take a symmetric Young diagram, so okay, this is not a conjecture. So if lambda is symmetric, now what you do is you look at Young diagrams inside lambda. Okay, then if you look at q to the power of mu, and mu belongs to lambda, the conjecture is that this is unimodal. So this problem, I believe, was first posed by Stanley in the 1980s. There has been some work done on this problem, but progress has been slow. I should say that the symmetry is necessary. If initially people thought that maybe it is always unimodal, but it turns out that it is not the case. So if you take a Young diagram 8844, this was an example that was found by Dennis Stanton in 1986. Okay, in this case, you don't have any modality. But if the conjecture is that if you assume it to be symmetric, then it has. Okay, and how is what I told you related to this? Maybe we can talk about that offline. Okay.
Questions? Yes, Madhu.
Okay, thanks a lot for the nice talk. So, so this connection between rank polynomials, which can be defined for arbitrary posets, right? And Ehrhart generating function, if that's more accurate. So that, how far does that go?
So, okay. So what you're saying is that, so you start off with a poset, and then, okay, there are many different polyhedral models that you can come up with. Are there, so there is the order polytope that I mentioned, chain polytope that I mentioned. Right. Yeah, what can we say about the Ehrhart polynomials and so on and so forth? Quite a bit actually. They have interesting, positivity properties. They have interpretations in terms of, yeah, so that's, that's the entire story there.
But this is a general factor that the rank polynomial of this of that lattice agrees, of that poset, sorry, agrees with the Ehrhart.
No. They need not always be Ehrhart polynomials.
They need not be.
They
So,
need not be.
so when are they exactly Ehrhart polynomials?
Yeah, that's a good question. Yeah, so yeah, I mean, it's certainly worth thinking about. So yeah.
But in this case, that's a crucial ingredient, no? Is it?
Yes. In this case, yes. In this case, you can write them as Ehrhart polynomials. That's correct. No, actually, no. I'm not saying. No, I'm not saying that. No, I didn't say that. So, no. No. So these are not Ehrhart polynomials. We're not saying that. What we are saying is that you can interpret, the number of lower ideals as lattice points in some polytope.
Yes, but that rank generating function doesn't it count that again? That it counts the number of lower ideals, no, of given size.
No. It's a bit different.
Okay.
No, it's a bit different. I mean, are these themselves Ehrhart polynomials? I don't think so. Because,
okay, not themselves, but more like, more like this connection. This is what I had in mind, probably. Yeah, more like what is used here. So the number of lower ideals corresponds to some the number of lattice points in a polytope. So this connection does this hold in general for one of these order polytopes, maybe the order polytope that you mentioned?
Correct. I mean, you can. It is the order polytope. Correct. It is the order polytope. Yes.
For which this holds.
Correct. Yes. So the number of lower ideals is the number of lattice points in some order polytope. Yes, that is correct.
They agree generally.
They agree. That's correct.
Okay, thank you.
And and that can potentially be helpful. Yeah.
And the Sylvester's method. So what does he use to prove this?
SL2, representation of SL2.
Oh, okay. Wow. That's nice.
So could you comment on this fence posets linked to like lattice path matroids? Sort of like the same, taking a walk in a lattice and you have this encoding of steps, like taking north. And so there's an encoding in terms of matroids where you start like, let's say from a lattice point, let's say the origin, and you want to go to Kn. And
is that a formalization of lattice path matroids or?
Like I haven't encountered. I've been reading about that, so it looks very similar to the fence poset structure. Like how have you encoded in terms of steps?
Correct. Yeah. I mean, we can certainly talk about this, but my understanding is that I think from this perspective, the questions that you ask are different from the perspectives that you would ask as a.
Yeah, like I've encountered them in terms of like matroidal subdivisions and whatnot. Correct. But the setup and the polytope and indicator functions, because there's a lattice path matroid polytope as well.
Right.
So I believe there could be some nice connections.
Yeah, absolutely. One thing is that there are certain things that work in this very special case, but how far can you extend them? And so, what is the correct extension, correct generalization? So, I really think that that there should be some nice follow-up work. So, yeah, we could talk.
And so just doing a sanity check. So, in terms of having two polytopes as unimodular equivalent, then the Ehrhart polynomials need not be same.
Oh, no, that's the same. Yeah.
That's the same.
Okay. Or even if you have a piecewise linear unimodular map, that's also fine.
Okay.
Because lattice points will be mapped to lattice points.
Okay. Thanks. Thank you.
Just a minor question. This ratio Rnq by Snq that you mentioned, it stabilizes as n tends to infinity. What do you exactly mean by stabilization?
Yeah. So, so what this is saying is that, so suppose you have some alpha n, some Rn by Sn, let's say that converges to some your favorite real number, say pi, okay? Then this thing is if you look at this Q deformation, so this is going to be some ratio of polynomials, and the leading coefficient will be non-zero. So you can write it as a Taylor series around 0. Okay. So this is some ank q to the power of k. Okay. right? And then what this theorem is saying is that as Rn by Sn converges to pi, you fix let's say the first coefficient. The first coefficient eventually become constant.
Okay.
I mean, it won't change. Then similarly, any kth coefficient will eventually become constant. So there's a natural way of defining a limit. And actually, there are some spectacular conjectures in this area as to, okay, so this is, I mean, one beautiful conjecture is that, okay, I mean, you have any real number, now it has some convergent Taylor series, which real number, and so the radius of convergence is always positive. But when is the radius of convergence minimal? And, so some interesting, questions of a number theoretic flavor. The guess is golden ratio, that kind of thing.
Sir, here you said that HLT and HLn minus t, they have same number of lattice points, right? And even same holds for their dilations.
Correct.
And like these are not necessarily isomorphic.
Correct.
So if we have two polytopes which are not isomorphic and they have same number of lattice points, so does this result hold in general even for their dilations?
No. As I mentioned, so what you could do is, you could do this, right? So you could just take the convex hull of k lower ideals, convex hull of n minus k lower ideals. So they have the same number of lattice points. But when you dilate them, then you don't have the same number of lattice points.
Okay, so in general, this may not hold.
No. Yeah. So it's I mean, it means a lot more structure. Yeah.
Other questions online? I can't see the screen, so.
I have one question.
Yes.
Yeah. So you mentioned that the leading coefficient of the Ehrhart polynomial represents the volume of the polytope. So for other coefficients, do you have some interpretation in terms
yeah,
of
no, it's unfortunately no. So it's a very frustrating thing we don't. I mean, there is a related polynomial called the 8-star polynomial about which we can see a bit more. But even there, so okay, so there are two classes of polynomials that you associate with polynomial. One is this things that come from lattice point enumeration. Ehrhart polynomial, 8-star polynomials for which we don't have good interpretations of the coefficients. Okay, and then you have these H polynomials and F polynomials and things like that. For these, we typically, I mean, there are characterizations, but the lattice point case, unfortunately, no. I mean, actually, yeah, people constantly make conjectures which are disproved. We only have nice interpretations in some very, very special cases, zoonotopes, there's a theorem of Stanley and so on and so forth. And if you so basically in this area, if there is a nice class of polytopes and you look at the Ehrhart polynomial and you give a combinatorial interpretation of the coefficient, then people will be very, very happy. So
thank you.
So these circular fence posets, that's something that you came up with, so to speak, right, for this particular problem.
Yeah, I mean, so we made a mistake in drawing, and then really.
Okay, but this is something you tailored for. I mean, you started off with the polytope, right? I mean,
no. We started off with the fence posets, and there was this thing that we had those various inductive things that we had to do, but we were unable to make it work. Let's try to maybe are there some ancillary objects and.
Okay.
And on the board, there was a diagram which got smudged. And so, okay.
Okay. So actually, in terms of your experience, so you started off with these fence posets, and then you realized that there are these polytopes, which this leads to that.
Exactly.
Who's Ehrhart.
We didn't start with polytopes. We started off with this with posets. Yeah.
Okay. Thank you. Thank you so much.
Yeah, along the same line, actually, I wanted to ask, how about some other posets, not really the fence posets? What goes wrong if we had not taken the circular fence posets?
Yeah, I mean, it's not a question of what goes wrong, but it's an amazing thing that it works in this case. And so, actually, the thing is, maybe we could talk about this over the course of this workshop. I mean, this is sort of a type A construction, that should be a type B, type C, type D construction. And so, so these are things that, I've just started thinking about, but yeah, we could chat about them. I mean, this is not something that you would generally expect.
Okay.
Miracle.
Other question is, what about if we had, so from a poset, if we come back to lattice, which has a more structure, so would the theory would go, I mean, much easier way, I mean, proofs and everything from a poset if we come back to lattice?
So here, the thing is, we notice, so you have a poset and then you look at these lower ideals.
Yes.
The lattice. But if you start off with a lattice to begin with, I don't know, I think these kinds of questions, I don't think the lattice structure is relevant. If you're doing something geometric, then maybe, I mean, maybe much better, but these are, I don't know, naked combinatorial questions. So I don't think the lattice structure is particularly relevant. So I don't know, for instance, I mean, in these kinds of things, you don't really use the fact that it's a distributive lattice or anything. In these things about Young diagrams. So, I mean, just use the fact it's a poset.
Okay. Yeah, thank you.
If there are no more questions, let's thank the speaker again. This ends the morning session, right? Or the what time is that? 11:30. Okay, so we'll meet at 11:30 for the first mini course lecture by Omidamani. Okay. Other than the reference poset for which this holds.